And then we tested another one. And the last thing is our microcapillary tower. And this one here has a very, very generous spacing between the individual windings. So you can barely see the microchannels, but you have a lot of area here on this glass tower that is not covered by the microchannel. And that is becoming important later on. Nevertheless, this is made out of scrap material that we found in the lab. This is almost a Hyakuen reactor, with the exception of the syringe pump, of course. Here are the dimensions that we need to compare. And this is the reaction that we did. Phenone, isopropanol, a sensitizer, DMBP. And typically 350 nanometer, you get an addition of isopropanol onto this double bond. And it happens stereoselectively if you have an R group there. Okay? So a very nice reaction, not discovered, but studied by Hoffmann in France. Same strategy. Know your signs, know your concentrations, and do the first conclusions from it. So what we have here is, this is a UV spectrum of DMBP. There's a very weak but important absorption here, this shoulder. This is the important part of the UV, not the big thing there. And these two lines that unfortunately are very faint are now two different light sources. We used a UVA lamp that came with the reactor, and we used an LED. And LEDs are a bit more tricky. We could only get at a reasonable price a 365 nanometer LED. So the second line here is the LED. The wider line is the UV lamp that we used. And so you have two different extinction coefficients that you're looking at. So you're getting two different plots in the Beer-Lambert's law, the blue one and the red one for the different extinction coefficients. DMBP is now added only in a tiny amount. So it's only really just a hint rather than a co-solvent like acetone previously. And there are four vertical lines here representing the path lengths for the four different setups. We used a test tube. The test tube cuts off here, 4.5 millimeters. The microchip has the most shallow, the shallowest microchannel, so it cuts off all the way on the left. And then comes the Drell device, and then comes the diameter of the microcapillary. But you can see that in any case, you always have complete penetration. So here, there's not much of a disadvantage in terms of the sensitizer for the Rionet, for the batch system. You still have complete penetration. So the molecules on the other side or inside the test tube get a chance to fetch some light and react. And these are again then the conversions, not the chemical yields, because here the product isolation is a bit tricky, in particular on small scales. So all we did is we determined conversions. The reactions are very clean though, we tested that. So there's no decomposition here. And for the batch reactor, 5 and 20 minutes, so 90% yields, 90% yields for the three cases after 5 minutes. For the Drell device, 80, 99, so for the phenone itself, a bit lower. For the other ones, the ether-containing ones, for the alkoxy-containing ones, a bit higher. But same, after the same time, not so much. Then the microchip, after 1 minute, already a good conversion. After 2.5 minutes, pretty much finished, again, except for the phenone case. And the microcapillary tower, 5 and 7.5 minutes. So if you compare the numbers, they're all in the same range, except for the microchip. The microchip seems to perform best. And again, you know, you have to be careful. Conversion is one thing. The other thing is, what are the parameters of the reactors? In particular, of course, the LEDs. The LEDs have very low power. 6 LEDs, 0.075 watt each. It's not very much. So again, you have to look at the irradiated area volume ratio, so the surface volume ratio that you always hear is good for microreactors, and yes, it is for all three microreactors. It's best for the microchip. And when you look at lamp power per irradiated area, here, of course, the weak power of the microchip gives a low number. So the impression is given not so good for the microchip. And you get the highest number for the batch system now and for the Drell reactor. This one here gives a low number because of the wide spacing between the individual wrappings, so there is room for improvement. All right. And then we calculated the energy efficiencies for all the 4 different ones, and here are the times, here are the watt hours that we learned again from Yu Sensei. And now the microchip gives impressive numbers here, a few orders of magnitude higher than the batch system. And also the microcapillary, at least, if you just look at it in general, gives a nice number. But if you just look at the capillary surface area that you have in your reactor, this number suddenly shrinks very dramatically. So it's important to really include the coverage of the light source into your equations. And then we calculated space-time yields again, and here probably we had the biggest surprise. So again, with our little equation here now indeed was foreknown correctly, and the irradiation times here, only the microchip now gave a significantly higher number. All right, all the other microreactors gave actually similar numbers to the batch system. So here, this common belief that the microreactors give, by definition, higher space-time yields doesn't seem to be really true. But all the combinations of light efficiency, space-time yields, and reactor dimensions or parameters obviously play together and may tip the balance to a better performance or more equal performance, batch versus microsystems. All right, so we're almost finished now. Just want a summary and conclusion. And the first thing is for the students is wake up. And the second thing is I want to give you some advice. I had an interview yesterday and I was asked what advice do I have to give to the students here. Follow your interests, not so much your dreams. Dreams are usually unrealistic. Follow your interest and stick with them. So I became interested in organic chemistry when I was 13, became interested in becoming a photochemist, and I became a photochemist, and I do not regret it at all. And the other thing is there is a real world out there, and that includes probably that you have the great opportunity to use science to go where probably you wouldn't really go. So if you want to come, for example, to JCU, I can only invite you. We can arrange definitely some project that is related to what you're already doing. And you know, you can practice your English a little bit and improve it dramatically. And you can also enjoy the Great Barrier Reef. And I forgot to mention that this is the heart reef, because one of these little island here, this reef here has the shape of a heart. Quite nice. And of course, scientifically, and this is again a personal statement, for me, photochemistry has been truly exciting. And because we are dealing with excited states, this is a real true statement. Okay? And I think that there are plenty of new things still to discover, not only by accident. I think that solar chemistry will definitely find its way as a dominant green technology if it just gets the political support that it needs. Science is more driven by politics rather than really by discovery or science. And you have to battle sometimes really a lot and struggle. I think that photochemically we can indeed make a lot of interesting molecules, literally, and I start to like this term, with a flick of a switch. On, reaction, off, reaction stops. And microflow photochemistry takes full advantage, I think, of microreactor features and has definitely the potential within the next couple of years, and Yu Sensei is going to the same direction, to become an interesting R&D tool for the pharmaceutical industry, for example, to try out photochemical reactions. Photochemical reactions give very unusual molecules that have never been screened. There's a huge pool of potential pharmaceuticals, new lead structures out there that haven't even been touched. And traditionally, I finish with this fellow, and I don't want to break with this tradition today. This guy is a pioneer of photochemistry, and he had a dream about 100 years ago. He dreamed of solar photochemistry becoming a relevant and the most relevant industrial process. And everything would be done in greenhouses rather than in factory buildings made out of bricks. Unfortunately, he was probably too much of a visionary. So his dream never materialized because we went to nuclear instead of solar, and Japan more than any other nation, probably knows also the dangers of nuclear energy. So if you want to take home a message, first of all, there's a real world out there, and wake up. And the other thing is take home this reference and read it. This guy is talking about not about bioenergy, mimicking plants and producing chemicals. So he's a pioneer in almost anything, everything, including green chemistry. All right, including sustainable energy, everything. So what is the future of photochemistry? Maybe a combination of micro and solar. If you have the money, you can just put your balcony here full of microreactors, and you can do photooxygenations in a microreactor, if you have the money. I want to thank a lot of people, and for the very first time, I want to include my chemistry teacher, Mr. Klein. I forgot his given name, unfortunately. I hope he's still alive, but he was a brilliant entertainer. I remember him doing experiments with sulfuric acid, and then he wiped off all the sulfuric acid on his lab coat, and was a great performer, inspired me a lot. Of course, my supervisors, Professor Matai and Griesbeck, and also Professor Inoue here, for being very good teachers and providing excellent research facilities. But also for allowing me to go abroad. In particular, Professor Griesbeck was very, very generous there. And as part of my students, I want to thank a few, in particular Oksana, who is working on the microphotochemistry together with the postdoc Alexander, a few of my Irish PhD students, and countless undergraduate and internship students. So we have frequent visitors from France, Germany, in Dublin, and also in Australia. If you want to come for a couple of weeks, why not? Give me a call or send me an email, talk to your supervisor. As I said earlier, we can definitely find a project that is relevant to you. And finally, I'd like to, of course, thank the funding agencies, and I'm pretty sure I'm way over time, but I wanted to tell my personal history, and well, here it is, and thank you for your attention.